Hello, everyone. I'm super excited to come here to present at this annual Performance Summit. Especially, I'm a software engineer on the kernel team at Facebook. I was in Bay Area before that, working in different companies for 18 years, and now relocated to Seattle, enjoying the weather, and today it's so beautiful. So today, I'm going to talk about BPF. So people ask, like, what is BPF? It's used to stand for Berkeley packet filters. Nowadays, it's not Berkeley anymore, and packet filters is maybe 1,000th of the use cases that we have. So it should be thought of as a technology name rather than an acronym. So underneath, it's effectively a generic virtual machine inside the Linux kernel. Its instruction set was selected that it has one-to-one translation from BPF instructions to x86 and ARM64, though there are JIT backends that are written already that translated to Spark, to IBM S390, to 32-bit Intel, and so on and so forth. The main difference versus why this instruction set versus, let's say, Intel, is because it's verifiable by the kernel. Kernel analyzes the assembly code that user space is passing in, and can make sure that it's safe. The main purpose of it is to extend the kernel. In this example, it's a simple, trivial Python. There are different languages, of course. The primary one is a C. So what this snippet of code does, it's in a runtime, takes this piece of C code that's embedded inside the Python as a string, compiles it on the fly on a specific machine, then gives it to the kernel to analyze. The kernel loads it and attaches it, in this case, to the sysclone kernel function. So every time a new process started, inside the kernel, the sysclone method will be called. This piece of C code is executing and saying, well, yeah, I'm doing hello. So what it allows us to do over the last six years or so, Brendan Gregg wrote a ton of tools. They're all based initially on BCC library, what stands for BPF Compiler Collection. Now the community is slowly transitioning to the tools that are BPF trace-based. That's yet another language that's similar to old Solaris dtrace, but yet different. And all of the tools are designed for single purpose with a Unix philosophy in mind. Do one thing and do it well. One of the popular tools, let's say here, will be the OpenSnoop, that you run it on the box and it shows like all open commands that all processes inside the systems are doing. It's super useful to do the performance analysis to see what is happening. Like exec snoop, as you can tell, like will be snooping all of the execs call in the system and so on and so forth. So this chart, eye chart, is can tell you, like, if you're interested in a particular problem inside analyzing the application or device drivers or anything else, it shows you what kind of tools may be useful for you when you're dealing with performance analysis. In Facebook, we have all of them installed on our production servers everywhere. People are familiar with them. Everyone has its own set of favorite tools. They use them all the time. Under the hood, BPF works like this. There is a program, typically small, written in C. It gets compiled by LLVM. Then this program typically embedded in a C++ service or other Python, you name it. It gets loaded into the kernel. Kernel analyzes it and uses different building blocks that are already present in the kernel, like maps, which will be hash table, array. There are all sorts of other primitives inside, and works together with the kernel to do what user requested it to do. There are two sister technologies to BPF that are relying on BPF. They are called XDP, which stands for Express Data Path, and AFXDP. XDP works completely in the kernel, where all the network packet processing happen inside. It doesn't go to the user space. Whereas AFXDP, the pre-processing is done by the kernel, whereas the rest of the work is done by the user space. FXDP in that sense is similar to DPDK, which is a full kernel bypass, but it still works together on a single box, and there are like major operational differences versus tools like DPDK that it allows us to actually use it in production. XDP is the one that running everywhere, all the edge network of the Facebook. It's protecting from the denial of service attacks. It's doing all sorts of firewalls, including our layer 4 load balancer. Quick demonstration of performance. So DPDK is a green chart here. It shows, as you can see, that on the one core, it actually has a small advantage versus XDP because it's really well tuned for like completely bypassing everything that the kernel built. Whereas with XDP, we're reusing and integrating well with the rest of the kernel. So there is some overhead that because of this more generality, but it scales way better when it goes further. Like DPDK is a polling approach, has to waste the core. That's why there is no 6-core number for the green line, whereas XDP scales better. On the bottom of the chart, you can see how XDP as a technology integrates with the kernel. The green bars are just a regular Linux kernel processing. You take like a router, and brown is XDP assisted, where performance is effectively, well, I don't know, 3x faster because of the less overhead and direct access to the packets. The thing I mentioned in the beginning, the kernel verifies all the BPF assembly that passes into the kernel. Two previous speakers mentioned the static analysis and how it's done in user space. The bad case of the false positives and the false negatives. So the kernel is also doing static analysis, but it's actually doing symbolic analysis. It's doing symbolic execution of the assembly code that user space gives to the kernel. And it's absolutely not okay for this analyzer, the verifier, to produce a false negative, because it's a safety issue. Like, it cannot say that, well, yeah, maybe like it looks okay, so let me accept it in the kernel. This is not okay for the kernel. It has to guarantee that the program will be correct. But what it means that in some cases there are false positives, and it will say that, well, I really don't know what you're doing here. It's probably not safe. That's why I'm rejecting it. Versus static analysis tools that user space are doing, if it is a false positive, the users will complain, will start ignoring this type of analysis. For BPF, they cannot. They simply, kernel just reject their program. They're saying, I want the kernel you to run this stuff, and if verifier is not smart enough, it just rejects it. So they have to fight it. So that's why, like, over the years, especially when we all started 6 years ago with this, people mainly complained about the verifier. They still complain. They're saying, oh, it's so dumb. How cannot it see it? This is what I'm doing. It is safe. I know. Like, look, it's like obvious. Well, it took a while for the verifier to be more human in terms of understanding what the human are trying to do in the C code, especially consider it's doing only with assembly. And only now we add in the type information to this assembly, so it's like strongly typed assembler in the future. But what I will say, that verifier is sometimes smarter than LLVM. For safety reasons, earlier this year, we had to introduce that code elimination pass to the verifier in the kernel. And while debugging it, I was amazed that fully optimized LLVM code with -2, even afterwards, the verifier is saying, no, these 2 instructions are dead. They will never going to be executed. And it just like removes the code, removes the branches. Well, turned out it was actually the case. Why this is happening? The purpose of the static code analysis and optimization is different. Like LLVM and compilers, they need to optimize the code to make it as fast as possible. whereas kernel needs to make sure that it's absolutely safe to run. Because of this, there is different take to the whole like static analysis approach. This year, 2019, was absolutely amazing for the verifier advances. Earlier this year, we finally solved the halting problem. Who knew? Let's take this example. So because it's symbolic execution, now verifier, like it used to just reject all the loops. It would just analyze the control flow graph, let's say, find the back edge and say, no, the loops are, I don't know what to do about them. Now it analyzes the loop. It sees that though it is a loop, it knows that it will terminate. In simple cases like this, 10,000 execution. Currently, the limit it does, it says like if it's less than 1 million instructions, it's okay. I know the critical path through the program. I know exactly the number of the worst case of the number of instructions the program will take, so it will accept it. A bit more complex example like this. Here, notice the volatile for the struct. It means that every iteration of this loop, the length field of the socket buffer will be different. So every time it will be adding either 3 or 7. So what verifier will do, it will run through this loop, analyzing all possible combinations through this loop and every exit condition. And in this case, well, believe it or not, 9, 10, 13, and 14 are the only numbers well, not only the numbers, but these are the guaranteed exit conditions. If the user made a mistake and, well, did 12 instead of 13, that would be an infinite loop. And verifier will actually catch it. This is still sort of simple. So this one I call a random number generator, again, because it's a volatile structure. Every iteration of the loop will be different. And in this 10 iterations, in these 10 iterations, since every bit will be randomly sort of set, the possible return values out of this function is from 0 to 1,000. So by itself, I told you that it will take verifier knows 1 million, up to 1 million instructions. So 10 iterations of the loop sounds small, but all of these loops, they feed into something else. Like what if result of this function is used as an offset into some data structure, into pointer, adding a pointer to some like kernel data structure. So now this range has to be checked. So the whole range needs to be understood by this verifier logic to make sure the subsequent access that using value of this function will also be safe, that it will not be hit in uninitialized memory. It will be like within the region that that particular pointer points to. So the way verifier is doing it is doing precise tracking. It knows when to switch from precise tracking of the scalars inside the program into more range-based analysis, combines all of the stuff, and at the end, we have a pretty powerful analysis tool. But also what we did, we detect use after free just as well. In this case, it's not only k-malloc, not only like malloc free styles type of use after free. In this case, we know that the socket, in this case, the lookup functions, it returns the socket, and release function, it may not actually free it. It's pretty much a reference counter increment and decrement. But from the use after free perspective, the ref count increment has to be paired with decrement. So the verifier, again, will go through the code, will analyze that there is no possible path at all guaranteed that the user wrote the program in such a way that will not be such a use after free thingies. Similar to this, we have deadlock analysis as well. The verifier will guarantee that if a program using spin locks inside the kernel, they will not come dangled, that every lock is paired with unlock. What about Facebook? So inside of Facebook, we upgrade the kernels very quickly. We're already deploying to production 5.2 kernel, which is less than several months old. We have upstream first philosophy. Every patch that we run in production, it will be seen by upstream. We push everything to upstream only when it goes through rounds of review, intense arguing on the public mailing list. Then it gets accepted upstream. Only then we push it in our Facebook kernels. That's why we have an ability to upgrade them quickly. The only thing that stops us from upgrading instantly is performance regressions. And that's where BPF actually comes to the help. We have roughly 40 programs running 24/7 on every server, and because there are many different tools already installed, like these BCC tools for performance analysis, a bunch of other tools, about 100 people run from time to time. What it means that there are tons of different programs running, and they all change the behavior of the kernel. Trace point one is the mechanism inside the kernel for particular. It's a stable mechanism to probe certain places, whereas kprobe is a mechanism where user can attach and run at any given point inside the kernel. It only needs to know the kernel function name to be able to change the kernel behavior at that particular point. Because of this sheer amount of work that is happening, BPF is always, well, at least that feels to me, responsible, because we give this power to the users and they just write a ton of stuff. And because, well, at the end, it's always a kernel team that has to deal with it. I will give you a few examples. So we have packet capture daemon. Initially, it was written many years ago when BPF didn't exist. It's doing, now it's all BPF based. It's attaching to the networking ingress packet processing pipeline, captures 1 out of the million packets and send them to user space for the further analysis. So it's really low cost. And turned out when we started rolling new kernel, in this particular case 5.2, we rolled it to, well, several thousand machines and realized, well, look, in new graphs, we always look at the, in this case, it was a thing like web tier, one of the web tier. The metric would be request, number of requests per second. And this number of requests per second was like 1% slow. We started investigating. Turned out that exactly, though there are like 40 plus different services with BPF running, this particular service was causing a regression, which was kind of weird. So like, why this one and not the other one? Turned out the answer was pretty easy. We just looked at what else is happening, and on these affected machines that are slower, the extra modules loaded. Turned out that the daemon not only using the networking mechanism of BPF, it's also using this tracing mechanism that are kprobe based, and a kprobe is unstable kernel API. The function was simply removed between 4.16 and 5.2 kernel, and this daemon tried to attach it. He didn't find it. Said, well, probably BPF is broken. Let me go back to the old style that was like 6 years ago. It loaded NFLog mechanism of IP tables modules. IP tables loaded. This started to affect every packet in the system. The whole thing like slowed down. Another interesting example, again, when we were rolling 5.2, we have a daemon that's doing all of the performance analysis for the fleet. It's also BPF based. It collecting the user stack traces, kernel stack traces, aggregates them, doing symbolization of the kernel symbol, user space symbol, collects them to data center, cloud analysis, aggregation, and so on and so forth. It was the last one. So while we were narrowing down what is causing this 2% CPU regression, it was the last one that we didn't turn off yet, because it's the one that's collecting all the performance metrics. And when we were like turning it off and using different mechanisms, just a regular like perf to collect the CPU analysis, we see that just that daemon alone is causing this 2% CPU regression. That was much harder to debug. It took, I would say, roughly about a week of people like scratching their heads, what is going on. And at the end, we were lucky that we did the perf runs with TLB performance counters. Turned out on the older machine that on the newer kernel, the TLB miss ratio is way higher. That caused us to look further, look into the kernel, what the mappings are for the kernel. Turned out that the daemon, because it's doing performance analysis, is using kprop mechanism inside the kernel that attaching BPF to the kernel function. To attach the kprop, the kernel initially, when it's booting, it's mapped with 2 MB huge pages, and attaching kprop make the kernel to shutter the pages and undo the 2 meg mapping into 4K. And because of 4K, everything was still working, but because the whole kernel text now in 4K, it will be miss increased, which increased the whole thing, increased the ratio of the user space, got slower down. So we fixed it. And the last example, I would say probably the most interesting one. In this case, it was about a month-long investigation. Different teams were involved. And for this one, I will go into details. So we have this security monitoring daemon. Again, bunch of BPF program, bunch of services are running on the host. In this case, it's a big database, one of the major ones inside of Facebook. And this particular daemon was also there deployed for the long time. And suddenly, after some time, people noticed that they have a huge spikes in P99 latency for this database. And it was really weird. They really narrowed it down that just removing, unloading this C++ servers and unloading like BPF programs, the P99 latency would go away. Database team involved, the performance analysis team, kernel team got involved, so everyone working on debugging. First facts, like what we knew. The database folks figure out that the mem copy, just a plain mem copy in user space, may potentially sleep for almost a quarter of a second. Just a mem copy. Well, clearly it could only be if kernel is servicing the page faults and it's servicing them for such a long time. What could be causing this slow page fault servicing by the kernel? It's contention. It could be a contention on this so-called memory map semaphore that kernel is using to protect memory region when it needs to modify it. When there is a minor fault, kernel needs to swap in the pages. It will grab the semaphore, bring the pages back, let the user space to continue. And at the same time, there are tools like TOP or PS that are using the proc interface of the kernel to read simple things like command line or environment variable, this particular process. Most of the people don't even don't pay attention to this type of stuff. And in this case, people knew that this daemon, the security daemon, is also reading it. But it's running with extra low priority, spending 100% of the CPU to do stuff, though these things are happening. So to figure out what's going on, we've dived into the kernel code, tried to remember what the heck this proc environ is supposed to do. There is a function called environ read that doing this access remote VM. So the next step is to bring one of my other favorite BPF tools. This one is called func latency. Again, combination of Python and C code. And what I'm asking this tool to do for the next 100 of seconds, please measure me the latency of this particular access remote VM function. Why this function? Because reading proc environ will call in into this function. And what I found here over the last 100 seconds, there were 10 cases where latency of this function was more than 128 milliseconds. So indeed, something is indeed reading the proc environ and sleeping for this long. The next step is to figure out what is actually reading this environment variable, because it can be PS, it can be TOP, it can be like any other tools that are running in production. Another tool to the rescue, BPF base, is called func slower. I'm asking it here to report me kernel, this -k and -u user stack traces when latency of this function will be higher than 200 milliseconds. The way it's doing it is loading BPF program into the kernel that captures start and end of the function, timestamp beginning and end, ignoring all of the events when the latency is shorter. When it is longer, at this time it captures the kernel stack trace, user stack trace, reports it back to me to the user space. Now I see that, yes, indeed, it was my daemon that spent 399 milliseconds just like trying to read this proc variable. Next step, another BPF tool, in this case, off-wake time. I guess we were lucky. So what you see here, the bottom of the stack trace is the user space code. Here it's doing the reading the proc, goes into the kernel system call read, all the kernel stuff, and what's the most interesting is on top. Here you see schedule call. Underscore schedule is what kernel is doing when it needs to put one task to sleep and schedule another one to execute on this particular CPU. So at the end, what it was really a priority inversion inside the kernel where lowest priority process was significantly affecting the most important job that was running in the kernel. Well, it turned out the answer was in front of us from the very beginning for months. This process, the combination of schedule heuristics that people tuned on the server and some other folks at the same time, they reduced priority of the security daemon to be, so it doesn't bother anyone. They reduced it from like normal priority to 0.01, and whole combination of factor caused this stuff. So fixing it in the kernel, which is not an easy fix, but the obvious one was just like change the priority for this process, and the problem went away. The takeaway is when there is an alleged BPF regressions, BPF-based tools are the best to tackle this type of problem. Kernel team also doing all kinds of other interesting investigation. And as I told you before, typically the services are done. There's a program. It's built inside the C++ service as a string, get compiled on the dev server, and gets deployed to the fleet. In the fleet, there is embedded Clang LVM that takes this stuff, takes the kernel headers that are present in the box, compiles them together, and only then it loads. What the problem with this approach is compilation itself on a host can disturb the main workload. And the other way around, the main workload can be occupying so much memory that compilation of 100 lines of the C code may take up to 2 minutes. And the service that is trying to start, or you're trying to do the performance analysis, like I'm logging into machine and trying to do my func latency script, it needs to compile 100 lines. It may take 2 minutes to compile this to 100 lines because the system is so overloaded. So that was the problem. What we come up with is what we call the BTF, stands for BPF Type Format. It's simple to the bones debug information that represents types, C types inside the program as the simple graph where it's represented as array with a 32-bit index that points what these types are. The main difference versus dwarf that it's much smaller. So we compile the Linux kernel with this type information. The dwarf that describes the kernel is 120 megabytes. The same format represented in BTF is 100 megabytes, so it's a small savings. But where it's really striking is deduplication. We come up with an algorithm to deduplicate all of this debug information. Is it possible to do it with dwarf? Probably, just much harder because the format is so simple. We take this 100 megabyte and compress it without losing any information into 1 megabyte. From there on, this information is shipped with the kernel itself, and it's loadable part of the kernel. The second part of this equation is the technology we call compile once, run everywhere. Now we can compile on one server, have the type information and assembly there. And on the production server, we have VM Linux, the kernel, with its own BTF information. We compare this to BTF and do adjustment on the fly. So if any of this is interesting, please hack on it. You have your favorite problem to solve. Please talk to us back. If you like it, we would love to hear. If you hate it, please talk to us. The feedback is a gift. We love to receive it. And of course, if there are like any new features that we would like to do, either implement them and send us patches, or just come to talk to us. BPF development is 100% use case driven. So your participation in the community is what's making the kernel better. Thank you. Any questions?
So how did you actually end up finding the, I'm Mukul, I work at Microsoft and Bing. How did you find out the difference between the 4K and 2MB? Like, was that, knowledge, or was it just the fact that, how did you go from more ITLB misses to just the fact that it was 2MB to 4K?
That's the only thing. Like, before figuring out that it's the mapping, like, we looked at a bunch of other things. We tried to bisect it, and bisection was just like too large to accomplish. There were way too many patches in the kernel. And at the end, we were lucky that just run not a regular perf analysis, not only like CPU cycles, but ITLB. And because there were ITLB misses were high, since it is at ITLB, there is nothing else but the mapping of the pages that can affect it. Because that's the only thing that was left to narrow down, the two different kernels, 4.16 versus 5.2. And we just looked at the mapping, and it was pretty obvious. But what caused this mapping, that was another day of investigation.
All right, looks like there are no questions. So thank you so much again, Alexei, for the talk.